Testing, hello. Hi. I would like to think that today's stream is going to be somewhat normal, because the internet seems to be somewhat normal. I actually did a test run like 20 minutes ago and it was not normal, but now it's becoming more normal. So good luck to us. Let's do this. Yeah. Normal is a relative word. Okay. So I actually just, I guess we need to do a recap of yesterday because a lot happened. Yesterday we went through this summarization one, like from the beginning, no, from here actually. We had loaded the data, that's the problem. The problem is that, we couldn't find a data set that would suit this situation, but when we did, then we got the ball rolling and we did some pre-processing on the data and what else? Yes, and now we're loading the metric, which is, I just like reran this because even the zip files were gone, but now they're back and I actually added the train as well. Yesterday was just test and validation, meaning I should probably update my, what I'm calling train here is actually the test. But like 30,000 rows, that's pretty good for, okay, I'm gonna update it. Wait, I'm gonna see if it does the split. If it does the split, then I'm not gonna update it, but it does not. If it, oh wow. Let's see. Yeah, we'll see. If we need something for evaluation, then that is going to be, I'll need to update it. Didn't I already do a login? I really do think that I already did a login right here. There it is. Why do I need to log in again? Oh well. There. Okay. So let me just read through what we're doing. Oh, video. Let's watch this video and then let's see what we need to do. And oh my God, even though dropped frame rate is there, you know what? I'm not going to be hopeful. It's fine. If the stream is unwatchable, let me know. But like, it's fine.
What is the Rouge metric?
Rouge.
For many NLP tasks, we can use common metrics like accuracy or F1 score. But what do you do when you want to measure something like the quality of a summary from a model like T5? In this video, we'll take a look at a widely used metric for text summarization called Rouge. There are actually several variants of Rouge, but the basic idea behind all of them is to assign a single numerical score.
Hold up, what did it stand for?
Take a look at a widely used metric for text summarization called Rouge.
Which is short, go back, go back. Uh-oh. A problem happened. How can I fix this problem? BRB. Okay. Okay, anyway, which is short for recall-oriented understudy for GIST. Okay, evaluation.
There are actually several variants of Rouge, but the basic idea behind all of them is to assign a single numerical score to a summary that tells us how good it is compared to one or more reference summaries. In this example, we have a book review that has been summarized by some model. If we compare the generated summary to some reference human summaries, we can see that the model is actually pretty good and only differs by a word or two. So how can we measure the quality of a generated summary in an automatic way? The approach that Rouge takes is to compare the n-grams of the generated summary to the n-grams of the references. An n-gram is just a fancy way of saying a chunk of n words. So let's start with unigrams, which correspond to the individual words in a sentence. In this example, you can see that 6 of the words in the generated summary are also found in one of the reference summaries. And the Rouge metric that compares unigrams is called Rouge1. Now that we've found our matches, one way to assign a score to the summary is to compute the recall of the unigrams. This means we just count the number of matching words in the generated and reference summaries and normalize the count by dividing by the number of words in the reference. In this example, we found 6 matching words.
I mean, obviously, like, one has to make metric, and this is as good as any, maybe probably better than most, but you know, like summarization, I guess I also saw that it compares to multiple reference ones, but still, I might summarize something very differently than the next person, you know? Like, the more ML and AI becomes natural, the tougher it is to evaluate them, right? Alan Turing should have added more tests, right?
Our reference has 6 words, so our unigram recall is perfect. This means that all of the words in the reference summary have been produced in the generated one. Now, perfect recall sounds great, but imagine if our generated summary had been something like, I really loved reading The Hunger Games. This would also have perfect recall, but is arguably a worse summary since it is verbose. To deal with these scenarios, we can also compute precision, which in the Rouge context measures how much of the generated summary was relevant. In practice, both precision and recall are usually computed, and then the F1 score is reported. Now, we can change the granularity of the comparison by comparing bigrams instead of unigrams. With bigrams, we chunk the sentence into pairs of consecutive words and then count how many pairs in the generated summary are present in the reference one. This gives us Rouge 2 precision and recall, which as we can see is lower than the Rouge 1 scores from earlier. Now, if the summaries are long, the Rouge 2 scores will generally be small because there are fewer bigrams to match. And this is also true for abstractor summarization, so both Rouge 1 and Rouge 2 scores are usually reported. The last Rouge variant we'll discuss is Rouge L. Rouge L doesn't compare n-grams, but instead treats each summary as a sequence of words and then looks for the longest common subsequence, or LCS. A subsequence is a sequence that appears in the same relative order, but not necessarily contiguous. So in this example, I loved reading The Hunger Games is the longest common subsequence between the two summaries. And the main advantage of Rouge L over Rouge 1 or Rouge 2 is that it doesn't depend on consecutive n-gram matches, and so it tends to capture sentence structure much more accurately.
Okay, I mean, it's more about, it's not about, okay. So if the words are there, even if they're all over the place and it's ordered in a wrong way, like grammatically, Rouge doesn't care, which is a good thing, but also not great.
Now, to compute Rouge scores in the datasets library is very simple. You just use the load metric function, provide your model summaries along with the references, and you're good to go. The output from the calculation contains a lot of information. The first thing we can see is that the confidence intervals of each Rouge score are provided in the low, mid, and high fields. This is really useful if you want to know the spread of your Rouge scores when comparing 2 or more models. The second thing to notice is that we have 4 types of Rouge score. We've already seen Rouge 1, Rouge 2, and Rouge L, so what is Rouge L sum? Well, the sum in Rouge L sum refers to the fact that this metric is computed over a whole summary, while Rouge L is computed as the average over individual sentences.
Over the summary? I should have checked for the length of the video before I took a bite out or something. Anyway, and no more videos? Okay, no more videos. Okay, let me drink something. shot myself in the leg. Okay. In comparison to the most of the other tasks we've covered in this course, measuring the performance of text generation tasks like summarization or translation is not straightforward. Yep. For example, given a review like, I loved reading The Hunger Games. That's it? Why does the sentence feel chopped off? Like, I loved reading Hunger Games. Okay. I loved reading The Hunger Games. What? Books or movies, you know? There are multiple valid summaries. Like, I loved The Hunger Games. Or Hunger Games is a great read, or like it's a good book. Clearly, applying some sort of exact match between the generated summary and the label is not a good solution. Even humans would fare poorly using such a metric. That's actually a good point. Like, create a metric that you could, I mean, obviously we're trying to imitate humans, but just rate humans first, because sometimes we're horrible at these things, because we all have our own writing style. For summarization, one of the most commonly used metric is rouge. I want to say rogue. Is there a difference in the spelling? Rouge score, which is short for recall oriented. So we have precision and recall, but this is recall oriented. Understudy for, is that I have a hard time reading this one. Is that a gist, or I'm guessing there's no such thing as a gist? Anyway, evaluation. The basic idea behind this metric is to compare a generated summary against a set of reference summaries, which are typically created by humans. To make this more precise, suppose we want to compare the following two summaries. I absolutely adored reading The Hunger Games. And then there is no adore. It's just as loved. I loved reading The Hunger Games. To be honest, this one is, it shows like, this is a 5 out of 5. This is a 4.5 out of 5. Yes, I am using the Goodreads score. Anyway, as much as I love the Anthropocene Reviewed podcast by John Green, like, I love it, I really do. I wish for it to come back. I don't like the 5-star rating scale. I prefer the 10 one. I have 10 fingers. I don't have 5 fingers. I like the decimal score. Okay. I don't even understand the 20. Like, normally we would get scored for 100, but then they made it 20. Like, I don't understand the 20 scoring system for schools. Or the 4. Like, that is the most ridiculous one. I think SATs are rated like to a 4. Just use either 10 or 100. That's it. You know? When you elect me, I will make sure that this happens. In other words, that will never happen. One way to compare them could be to count the number of overlapping words, which in this case would be 6. However, this is a bit crude. So instead, rouge is based on computing the precision and recall scores for the overlap. Yeah, at least we are computing different things. Don't worry if this is your first time you've heard of precision recall. Actually, it's not. We'll go through some explicit examples together to make it all clear. These metrics are usually encountered in classification tasks, so if you want to understand how precision and recall are defined in that context, we recommend Scikit-learn's guides. One of them is it's about false positives, and then negatives, and false true, positive, negative, basically. That I have heard about it in that side. For Rouge, recall measures how much of the reference summary is captured by the generated one. So how many true positives there are? That's recall. If we are just comparing words, recall can be calculated according to the following formula: number of overlapping divided by the total in the base. But okay, so we're just using different things to compare. This one's comparing it to the in the target, you know, source target, like that. For our simple example above, this formula gives a perfect recall 6 out of 6, which is a 1. All words in the reference summary have been produced by the model. This may sound great, but sometimes it has to do with overfitting, actually. Having perfect recall is not always great. Imagine if our generated summary had been, I really loved reading The Hunger Games all night. This would have been a perfect recall, but this is arguably a worse summary since it is verbose. I didn't know the word verbose meant repeating stuff, does it? Using or expressed in more than needed, meaning it has too many words. Okay, good to know. I think the stream is like fairly reasonable right now, like it's watchable, I think. Don't quote me on that. Okay. All right. Precision, number of overlapping divided by the total number of words in generated summary. Applying this to our verbose summary gives the precision of, okay, so recall says you're golden, precision says not, stop right there. 6 out of 10, which is considerably worse than the precision of 6 out of 7 obtained by our shorter one. In practice, both precision and recall are usually computed, and then the F1 score, the harmonic mean of precision and recall, is reported. So we can do this easily. We can just call Rouge and then, is that a test? Generated summary. So where are we? I already called Rouge. Oh, we have something. Did I run it? No, I didn't. If I run it, is it the same? Oh, it is not, because I'm using a different data set. Hey, that's fun. Rouge 1, 92. Rouge 2, 72. Rouge L, 92. And then we have 92 for the sum. What is Rouge 2? Is it the precision? Because that's the worst. Dot mid. That's funny. So their mid was we have perfect recall 0.86 precision and a 0.92 F1 score. What happened? There is no mid. Have I not called something? Let's see if Gemini can give us an answer about this issue. There's a lot of, actually mine, this one already has it, but mine didn't. It's all right. Dataset actually computes confidence intervals for precision. Mine didn't though. Aggregate score, mine just gave me one thing and it's like, here you go. Be happy. Low, mid, and high attributes, however, okay, Rouge 1 is a variant of, is the overlap of unigrams. What was Rouge 2 though? Maybe they talked about it in the video. Oh yeah, okay. Now what about the other Rouge scores? Rouge 2 measures the overlap between bigrams. That makes a lot of sense actually. Yeah, I know what bigrams are. I mean, yeah, I'm happy that this blog explains things. Bigrams means pair of words. Neighboring words, only 2 though. While Rouge L and Rouge L sum, why do we have mid and then we have L? This is too much for me. Measure the longest matching sequences of words by looking for the longest common substring. Oh, really? In the generated and reference summaries, sum in Rouge, sum is regarding summary, right? Refers to the fact that this metric is computed over the whole summary, while the L one is computed as the average overall individual sentences. Okay. Try it out. Okay. Create your own example of a generated and reference summary and see if the resulting Rouge score agree with a manual calculation based on the formulas for precision and recall. I'm good. We'll use the Rouge scores to track the performance of our model, but before doing that, let's do something very good. Something every good NLP practitioner should do. Ooh. What was that?
Muajab poll just followed. CL welcomes you.
Muad, right? Muad Zabur. Whoa. Hi, thanks. Thanks for the follow. If you have the energy, say hi in the chat. If not, that's cool. But still, thanks for the follow. Every good NLP practitioner should create a strong yet simple baseline. What are we creating a baseline for? What are we doing? So, okay, let me just check where we are in this blog creating a strong baseline, which is for the metric, and then we start with the fine tuning, which I'm guessing comes here. Okay. So a common baseline for text summarization is to simply take the first 3 sentences of an article, often called the lead 3 baseline. I actually know nothing about this. We could use full stops to track the sentence boundaries. But this will fail with like United States or UN or what else is there? Doctor, stuff like that. So instead we'll use the NLTK library, which stands for Natural Language. I forgot what the TK stands for. But like this is like one of the most famous and most well-used libraries that are out there. Let me just Google it for it. Oh yeah, the mid issue. It just didn't have it. Yeah, I thought so. Thank you. So let's get our NLTK. What do you mean it's already there? I don't trust you. Natural Language Toolkit. TK? Toolkit? Yes, includes better algorithms to handle these cases. We can install it as such. We can download it as such. Honestly, one of my goals in life is to go over the NLTK, what is it called? There's a blog, a tutorial, but I think I might be mean, but it is like one of the best things for base NLP knowledge. But even though we can use it within things, I don't know if it's I don't know. Is it a toolkit as in for processing, or is it a toolkit for training, you know? So that what is something that is I wouldn't say it's stopping me, But yeah, the only thing that's stopping me is me. That I know. Because I probably have that, I'm gonna learn the NLTK library. I don't know, like I've had that for 5 years. And just like saying I'm gonna try to learn NLP better. If I had not started this stream, I probably wouldn't have the energy to just continue doing something for over a year at a pace that I have been doing, even though it's not perfect. That I know. I've taken like 2-week breaks, but I'm still here, and that counts for something. So we import a thing, which is a sentence tokenizer from NLTK, and create a simple function to extract the first 3 sentences in a review. The convention in text summarization is to separate each summary with a new line. So let's include this and test it. Let's do that. I didn't know about conventions. So we're using punct, which I'm guessing stands for punctuation. Worst iPhone charger ever. That's funny. The charger broke. The charger head broke after they used it for 5 times. Why is the T capital? Terrible quality. Oh, we couldn't filter the 2 sentence thing? All right. Okay. This seems to work. I mean, we have our sentences, but nothing works yet. Now let's implement a function that extracts these summaries from a data set and computes the Rouge score from the baseline. Are we actually, like, what are we doing? Baseline. What are we doing that for? I don't really understand what we're doing quite yet. We can then use this function to compute Rouge for the validation and prettify them. Oh, prettifying is fine, but like, are we comparing the titles with the body? I guess we are. That we're computing Rouge score for human things. Let's prettify them. I'm guessing it. Oh, come on. Sorry, we don't have a validation data set. Let's add a validation. Shoot, why did I do that? Why did I do that? I do that to myself. Okay. Crisis averted. Anyway. We don't have a validation data set, so we need a validation data set. Let's add a validation data set. Here's our test. To get validation, I'm guessing we call for validation. Did I already did that. Did we do it for all of them? No. Extracted files? No. Okay. So I'm gonna need to do that for the other one as well, for the validation. I could probably put it in a loop, but we're not there yet. Validation. Show me that it works. Did it work? Yes. And then I need to append it. Do I say validation? Would that work? I don't think so. Oh, alaikum assalam. Hi. Zainul Abidin. Oh, sorry. Help me pronounce your word. Your name. Yeah. Hello. Happened. BRB. Okay, we're back. So, yeah, I need to call append. I like using ChatGPT, honestly. Append. I'll give it this code and ask it to append. I can bring the app here. Help me append the validation to the test. Actually, why should it be test? Why can't you use training? Would that take too long? Probably. Okay, the test. Split of the data set. There you go. Like that. Combine like that. All right. Merci. Thank you. Assume. Yeah, they do. All right. I'll do that. Concatenate. We have it all. What is with the train? What is with this part? No, I'm not. Oh, actually, wait. Yours was called. Is it called train? Even inside? I have no idea. Let's just KC this and try and test it. And if it fails, it fails. It failed. Because I think we're not supposed to do that. Let's try again. Uh-oh. Give me a second, wait. Let me just try to run this part. Take a look at the data set. Is it called train? It is called trained, huh? Asked the wrong question. I need the two splits. Don't combine them, please. That is what I wanted. I think so anyways. So we have load these two. Ah, like that. See, you should have told me that. It's your fault for not telling me, duh. It's not my fault for not thinking. I'm allowed to not think. Done. Yeah, we did it. Whew. I'm not gonna call you test. I'm gonna call you train because I'm lazy. Oh wow, hi. What are we doing? There's this blog and it's teaching us how to how to fine-tune summarization language model. So like you give it a text and it makes it smaller. Real. You really are the real. And yesterday I was struggling with the data set because I couldn't find the one that they were using because it was dead, Amazon reviews. but thanks to yesterday's chat, we fixed it. And today I'm just like going through the code. So I'm guessing this one should work. No, I just loaded everything, meaning I'll need to do the just gonna say run everything again. Run before. That's probably gonna take a minute. And if it's gray, it means it's running. You guys can't see it. I can. When it's no longer gray, I'll get back to it. For now, I'll just go through the blog. So it said we can use this function to compute over the validation set. Yes. Oh, come on. Why this issue continues to happen? Like, I don't understand. Why does my face continuously go away? I'll try for another BRB, but I'm sorry. Like, it's annoying that it happens every 5 minutes. Are we back? Yeah, cool. So we can see that row 2 score is significantly lower than the rest. Oh wait, no, I haven't. Oh, error. Oh, that error is normal. That's KCU. And then we don't need to install, it's already there. And then, oh, careful. What is with the error? Ah, there is probably no longer an issue. So let's see what. It's taking a while. That's fun. So, oh my God, 16 and 15. What is that? It's significantly lower than the rest. This likely reflects the fact that review titles are typically concise. So that leads, so that the lead 3 baseline is too verbose. We're comparing the whole thing with the lead 3, or is that just the lead 3? Oh, wow. Thanks. Thanks for the subscription, Dave. I don't normally get notifications when someone subscribes, but when I do, I say thank you. So thank you. Yeah, if you have. The thing about YouTube subscribing is that you don't know if the person who's watching this video or another one. Yeah. So we have a good baseline to work from. Let's turn attention to the fine tuning. There's an error. I don't like that. Oh, no. Mid, we don't need mid. Mid is not there. There's no mid. Can we just call it F measure though? Let me try, because we don't even have F measure, I think. Because like, it's just rouges. Like I can call rouge 1 or something. Yeah, we don't even have F measure, so I'm just gonna call U. Fine. Oh, thanks. You were watching this video. Hi. Okay, we have it. Yay. 18, 10. Ooh, that is rough. And then 17 across the board. The rest of the board. Okay. So we went through the metric part. Should we continue or not? Should we go to, oh my God, I am scared. Nope, I'm not going to continue. This is way too much. Nope. Take me out of here. Oh, wow. Even with the fine tuning, we're doing it with the trainer API and then with accelerate, which is actually fun. but I am too scared to do it. So I'm gonna run away and watch a video. Oh, it's not our normal professor. Today's NLP lecture is lecture number 11. So we are technically almost halfway there. Because there are 21 lectures. And this one is about distillation, quantization, and pruning, things that I have no information about. Another one, like I'm just like going through the titles. The one that I'm excited for is, this is more about linguistics. Oh, I'm excited for that. And then multilingual NLP, like that one is the one that I'm most excited for. We have a long way to go, but inshallah we'll get there. I'll have to believe that whenever that is. I really do think that my base knowledge is far more different than it was when I first started this learning. So I'm happy about that. And let's play the video. The audio should be okay.
Okay, so I'm here substituting for Graham
Oh my God, the audio was great because the guy has a loud voice compared to our normal professor.
today because he's traveling.
Good for him. Yes.
And yeah, we can just get right into it. So as everyone here knows, NLP models now are like really deployed at a large scale. And we all know that training big models is expensive. I'm sure that you've experienced that in homework 1 and in anytime you train a network, a deep network, you need GPU resources, and this is something that we all understand. But something that I think is overlooked is that inference. So once you have a trained model, now deploying it and making predictions for users is arguably even more expensive. Like if you look at the lifetime of a model, it probably exceeds the training costs according to this analysis within just 1 week of use. And so if your model is being used for months or years by many people, the cost will like greatly eclipse the training costs, which is.
That's a good point. The cost of just the cost of maintaining ChatGPT for normal use, like you would be surprised that it's free. Like I understand why Cloud Sonnet has such a limit on it, and the fact that ChatGPT doesn't is surprising.
More of a one-time cost. And this is a problem because if we want to make AI systems able to help lots of different people in different places, people without as much resources or access to power, we want to be able to reduce the cost of serving AI systems to the public. And this is also getting harder because models are getting bigger. There's been like maybe a slight shift towards reducing model size a little bit in the last maybe 2 years, but these models are still like billions of parameters in size, and that is expensive to serve. So the main question of this that we'll be talking about in today's lecture is how can we cheaply, efficiently, and equitably deploy NLP systems without sacrificing performance? And there's like a clear answer here that I'm kind of leading towards, which is model compression. And model compression here basically means taking a trained model and then reducing the size of that model before deploying it. And there's 3 high-level ways that we'll talk about in today's lecture for how we can compress models. The first is quantization, which is you basically don't really change the architecture or parameters of the model up to a certain amount of precision, and then you throw away the remainder of the precision. The second is pruning, so throwing out entire components or parameters of a model. And the third is distillation, where you might change all of the parameters, but you're basically condensing the knowledge of a big model into a smaller model that is retrained often from scratch to replicate the behavior of the big model. And don't worry.
Question on quantization. I remember something about changing bits from a Stanford lecture that I think I shared on Discord a few weeks ago. Like training it using 16 bits and then later doing 32 bits something. Let's see if that's close, because that's what my mind is going to. Okay. Distillation, we've heard about Distilbert quite a bit, but I don't know how to do those stuff, even though I've heard of them. I need to test something on my screen. Test finished. Back to the video.
Worry, I'll go into much more detail with all these things.
Okay. Did the video stop? What happened? Did I stop the video? No. Wait, what is happening? Oh, okay.
I think the mic stopped working, so I'm going to speak up. If anyone's having trouble hearing me, just please raise your hand. And yeah. Okay, so I've motivated this idea of model compression, which is very tempting, right? Just take a model, make it smaller, get the same performance, and
my brain is thinking, just zip it, like a normal file. Is that possible? That would be cool.
It's just cheaper to serve, right? Nothing about that seems bad. So I think there's a natural question of why is this even possible? And specifically, I think a natural question is, instead of taking a big model and making it smaller, why not just start with a small model and train it as such? Like that seems a little more intuitive. So that's the first question, is why not just start with a small model that we train? And then the second question would be, why is it possible to take a big model and throw pieces of it away without sacrificing accuracy? That does not seem like a given that should be even possible. And I'll just give you a little intuition for why this is possible. So this term overparameterized means, how many people are familiar with this term? You can raise your hand.
Having too many parameters?
The basic the meaning of this term is that you have a model that has usually more parameters than you have training data. Or more, in more casual terms, you just have a lot of parameters, like way more than statistical machine learning would say you need. So for example, like GPT-3, the original GPT-3 model had 170 billion parameters, which is like definitely over-parameterized. And so there's been a lot of work in the theory community of ML that shows that over-parameterized models that have a huge number of parameters, are actually much easier to train, especially for very complicated tasks. And the basic idea is that training deep neural networks for most tasks requires optimizing a non-convex objective, which is not guaranteed to, you're not guaranteed to find the global optimum of a non-convex objective. But when you have a bunch of parameters and you're trying to basically tune the parameters to find the best value of your objective, having a lot of parameters sort of lets you sidestep around saddle points or local optima that are not global optima. You can basically like take sort of shortcuts around barriers in the optimization space. This is sort of the intuition, and the CMU's convex optimization class goes into a lot more detail for this kind of thing. Anyways, I think the intuition here is that
I really have had a hard time just following this, so letting you know that is going over my head.
Models with a lot of parameters are easier to train, and they lead to better models. Okay. But you probably don't need all those parameters for inference. They're more of a training time trick. Okay, so now, before I move on, any questions about the motivation here?
Oh, I'm absolutely the kind of lecturer that says, stop right there. Hi, coffee. Nah, I'll be a chill lecturer when I become one. Because I do plan on becoming one. Just not now. Because like I did some assistant lecturing, and I think I probably wasn't like older by a few years, and it's a bit uncomfortable when your students are the same age as you. So let me be, I don't know, like I assume I am, I'll be like 10 years older than bachelor students in a few years. So that's an okay place to start, but that's still early, especially because I want to make money, and I know being a lecturer does not equal making money. So I'm good. When I feel like I have money to waste, then I'll become a lecturer so that I can give back to the community. See, I'm so generous. Anyway.
Okay, so we'll start with quantization. And the most obvious way to do this is post-training quantization. So you train a model as big as you want, and then you just reduce the precision of, say, all of the weights in that model. So, for example, where we can revisit this slide that Graham had shown two lectures ago on if you have a 65 billion parameter model like Llama 2, and you have, say, 4-bit precision, so 4 bytes of precision, so like 32-bit floats. Just loading that model into memory would take 260 gigabytes of GPU memory, which is more than most single GPUs that you could buy have. But if you instead reduce the precision of the parameters of the weights in that model, you see like a pretty massive decrease, which is linear to the reduction in precision. At the most extreme case, if you replaced each float 32 with a single bit, so 0 or 1, then you would only have like an 8 gigabyte model, which you could probably load into most GPUs. And so I think there's clearly an attractive proposition here in terms of the cost. But before we go into some of the nitty-gritty here, just a refresher from computer systems. So neural nets typically represent weights as floating point numbers in order to express, to have a broader range of values in the model. And so floating points, in at least in like the IEEE standard, which is the most common, you have 3 pieces. You have like a sign bit, which says is it positive or negative, a fractional bit.
Oh my god! I felt like I was transported back into. I remember the lecture where the teacher would like say, "This is the sign one." Aww. Wow. Oh, I missed that lecturer who was saying those things. Or maybe I'm just confusing them because I remember one. And I just remember in his lecture learning the word heap, like pile, heap. And I was like, huh, I didn't know that English word. Okay, now I do.
Which a fractional piece, which specifies sort of the it specifies the range of the values, and then the exponent, which scales how big or small the float is. So we can give an example here. So here we can do float 16, where we have like 10 bits of fraction. So this gives a lot more range of what the number could be. Then the exponent bit is 5, so you have up to like 2 to the power of 5 or 2 to the power of negative 5 as like the scaling factor here. And then the sign, which is positive 1 or negative 1. And so float 16 is pretty common, but for machine learning, it's often not enough because especially when you're trying to train a neural net, you often have very small or very big values like underflow or overflow. And therefore, a really popular data type that was designed just for machine learning is called bfloat 16.
Yeah, I hadn't heard of that. I was like, whoa, this is really well Organized. Mm.
which just like moves. The idea is you're just moving some of the bits from the fractional part to the exponential part, so you can have a larger range, but within that range, you may have a fewer choice of values to choose from. But it just works. It supports like some of the problems that we face in machine learning. Anyway, so this is floating point types, but as you can probably imagine, once you get below 16, you're really impacting the amount of things you can represent in a float, given that you need like one thing for the sign. And then if your range of the exponent is small, then you don't have that much of a range of values you can represent at all.
Okay.
So
I think my world shattered when I learned about base other numbers. I'm sure we learned it in school, but I did not retain the information. And then we had a class just called logic, I think. Probably not. That's what we called it. I learned about other bases. It's like, oh my God, this is beautiful.
popular way to like get really small amounts of footprint in models is by quantizing to integers. And this is not that obvious because you're taking a float and turning it into an int. And so one way this is done is called abs max, or absolute maximum quantization, where you basically map each
Someone give the word abs max to TikTok. They will run with it.
number in a list of floats to a range of integers. So for int 8, the range would be like -127 to 127, because that's 255 total values, and 2 to the power 8 is 256. And here you basically find the absolute value that is largest in the whole array, and then that becomes 127, or whatever the largest value in your integer range is. And then everything else becomes assigned to the closest integer that's like scaled by that value. So here, for example, in this example, we have 20 is the largest value, and so 20 would become assigned as 127, and then everything else would be assigned proportional to that. So like 0.5 is 1/40th of 20, and 1/40th of 127 is rounds to the nearest number of 3. And so this is kind of how you can go beyond floats and actually represent parameters with ints. The most extreme example, which should also now highlight some of the issues with this idea of post-training quantization, is what if we just had a binary value for every parameter, 0 or 1? And so instead of so we might train a
Okay, but is it possible? Because that would be fun.
model using floats, and we get these parameters. So we have the purple here is like the hidden states, and then the red would be the activations. And these are all between 0 and 1, right? But if we now round them to the nearest value, 0 or 1, we get on the top there a list of binary values. And this seems like really attractive, right? Because you only need 1 bit per vector. It's like really small. But now let's consider like a real example here where we are trying to do translation, and then we are producing these float valued hidden states and activations. In this example, if I just rounded up or down each of the values, the output vectors the embedding vectors that we would then decode to outputs, even though they're very different in the original float space, they actually become all the same thing here, which is definitely not what you want. So basically, by reducing the precision, you might be like significantly impacting the range of things you can express, and this basically does not work. Like
1.8 bits per weight? Huh. Is that possible? Wait. When 1.58? What? Huh. But was that possible? How?
turning a complex set of floats, of high precision floats, to binary numbers does not work. And later I'll show that there are ways.
Like, it's not that black and white. It is gray. So we need some non-zeros and non-ones
to make this work that are a little more complicated. They just require more processing after the initial training of your model. Okay, so now that I've motivated this problem, we can talk about a few like methods that actually work for post-training quantization. The first one is belongs to a class of methods called model-aware quantization. And the idea here is that if you can study the statistics.
This reminds me of content-aware something in Photoshop.
Your model, you can sort of learn ways to represent values in a way that is matching the actual learning, the actual distribution of weights in that model. So for example, with BERT, most of the weights in each layer are concentrated around like the mean value there, and you have a few weights that are very far from that mean value. So you can sort of fit a Gaussian distribution, normal distribution, to the distribution of weights. And then only a few weights in each layer will be at the tails of this distribution. So the idea here is that, therefore, and for just to motivate this a little more, if you have values at the tails of the distribution.
Oh, wow. I didn't know it's called that. Not binary, but ternary. -1, 0, and 1. The bitnet paper? Why does this remind me of quantum computing? Like, is this word used there as well? A recent paper that got really close to 1 bit weight, and like the models are usable? That is so cool. Because I know like there's the fight of making use of as little data as possible with models, but also making the models as small as possible. I like that. Like, I don't think I will ever work there, but I'd rather work with data, but I like it.
They pose issues for quantization because, like, if you're using the abs-max quantization I mentioned before, you're now defining your range according to the minimum and maximum values. And then everything in between, which might be close together, will now be grouped into the same bucket. And that throws away a lot of the ability to distinguish between weights in your network. So the idea here is that you basically store the outliers separately, and you actually store them in full precision. So you're like paying the full storage cost for a few parameters. And then everything else that's like sort of concentrated together gets quantized into a much lower precision space. And I think that this is, at least in theory, very effective, and they have strong results here. And however, a problem with that approach is that you're defining like the outliers and the minimum and maximum for each layer uniformly. So instead, this LLM.int8, which is actually very popular in NLP, you might have heard of it if you have been building NLP systems. They go a step further, and they, instead of quantizing each layer uniformly, they quantize each row or column of a vector in matrix multiplication separately, with the motivation that most of the parameters in transformers are for matrix multiplication. And so by doing this, they're able to actually get a better quantization because you're able to like have a more precise space range of the values for each row or column of a matrix. Yeah.
Just curious, in the previous slide, why exactly is the frequency range changing based on the layers?
Based on the layers? Different layers might have more concentration of weights to a single value, or like the values of weights in that layer might be concentrated or might be more broad. I think that's how to think of it.
Is that inversely proportional to the layers in the front? Like, because the layer 5 has a very high frequency compared to layer 10.
Mhm. Yeah, I think that's right. I think that the this paper also discusses that problem, that as you get later into the layers of a network, you see a lot more of these outliers, these large magnitude values. Okay, so moving on here, the last thing I'll say is that there is like an overhead you're paying when you're doing this kind of quantization, where you have to, for each vector, you are now mapping it to a list of numbers, and you need to then decode those numbers back into floats, like decode your ints back into floats. So there's an overhead that costs time when you're doing inference. So if you have like a small model, this is not going to help you go faster, most likely. But if you have like a really big model, it can actually like double your inference speed at least. And it also lets you load models into memory that you otherwise would not be able to. So there's like definitely a trade-off in when or.
So if your model is like huge, it speeds it up, but if your model is a moderate size, it makes it slower?
This is really desirable. Any questions here before I move on to some more high-level stuff on quantization?
It's really loud.
So
I mean,
in terms of,
it's really quiet. I don't know why Graham's lectures felt different. Like, he's loud and there isn't as much outside voice. So I'm guessing he's wearing a microphone.
hardware concerns, I think one of the challenges, like if you're somebody who's interested in algorithms, you might have very creative ideas for how you might do quantization. But the problem is that the ability for quantization to actually be effective or make things faster is largely limited by both hardware and also like low-level systems like the framework like PyTorch that you're running your models on. So at a hardware level, some data types are like basically just not supported by hardware. Like int3, like a 3-bit int, is not something that processors generally support. So
but it does
if your
exist.
quantization method uses int3, it's effectively just using int4, and then you're not getting a speed up there.
Oh.
And then PyTorch has its own requirements. Like PyTorch doesn't have int4. A lot of modules don't support quantization at all in PyTorch. Like something like an RNN, which is now like becoming popular again. It's not really supporting quantization right now. So you definitely, if you're trying to go this route for a practical application, you'll want to know what your hardware is, what your framework is, and what you can actually support with the ways you want to compress your models.
Oh, wow. By directional podium mic? Probably. Oh, he's not going and writing stuff in the background. Yeah, maybe he's just standing there. There is no camera on him. So.
And one last thing I'll say is that both of the methods I showed so far, they both have to like they have their own customized hardware accelerators that they wrote to make those things work. And this is like a lot of work, and most people probably don't have the time to do.
Ah, okay, there. So it picks up more of the background noise. Omnidirectional mics.
This. So there are methods that I haven't shown here that do quantization in a way that is effective without having to rewrite your framework or your hardware accelerator. But this is definitely something to consider with quantization. Okay, so now I think I've motivated why post-training quantization is hard, because you're throwing away precision, which can make it hard to get the most out of the network that you have trained. So a tempting idea here is now we know that, let's say we know we're going to quantize our model. Let's train the model with quantization in mind. And now we can revisit the example I showed before of binarized neural networks, which like didn't work. But it actually can work if you train with the binarization in mind. So a paper in 2016, they considered a case where all of your weights were -1 or 1. Activations are also -1 or 1. And they do some like clever statistics to make
I'm guessing you're talking about this.
that work. And then the gradients that you backpropagate through the model are also negative, like they're also discrete. And so it's probably kind of surprising that this works, but they basically are using the core mechanisms that we use to train neural networks and using fancy statistics to make this work for binary values. And by doing this, they get like kind of shockingly good results. Like on CFAR10, which was a very popular image classification data set for a while, they get like a 10% test set error. And at the time, like a state-of-the-art method was at a little under 12%. Like they're basically matching or beating some of these extremely strong models at that time.
That's crazy.
And they used effectively the same architecture from some of these models, but just binarized. So this was sort of a proof of concept that if you quantize during training, you can match performance and get a much smaller model, which I think was a really surprising finding.
I would like to know how much smaller. I don't think this is a performance and not size. Because like if it works, then why not try to use it? Global warming, people.
And then a more recent work that I think is really cool is that.
Hello. Oh my god, hi JSS. It's been a while because I was gone for most of the time. And then, yeah. And then I'm somewhat back, I think.
For doing quantization, another thing you can do is you can start with your model that is full precision, not quantized. And then you can basically train each layer, one layer at a time, to replicate its counterpart in the full precision space. So you can like run inputs through the full precision model. You get the output, the probabilities of each word, for example. And then you replicate your quantized model to reproduce, to get very close to those same weights. And then you do this at the second layer. So now you have like the logits from the hidden states from the second to last layer, and then you train your quantized layer to match those hidden states, and you keep doing that all the way down. And I think the intuition here is that by doing like a layer.
So I came to the YouTube side because the restream doesn't show the what is it called, emotes, and then I found out that YouTube allows question answering and polls. I honestly didn't know, and I'm out here asking you, did you know that? And some of you seem to already know, which is cool. Nice. The votes are coming in. We are counting them. Oh, is there end poll. Do I end it manually or do I just let it continue? I'll let it continue. That's cool. Oh my god. I almost dropped the mic. Sorry about that.
Layer by layer down. And I think the intuition here is those hidden states, and you keep doing that all the way down. And I think the intuition here is that by doing like layer by layer distillation, you're sort of replicating not just the output, which is kind of sparse and hard to replicate, but even the like the flow of data throughout the whole model step by step. And you can replicate that into the quantized model, which may run into issues when training just end to end.
Okay.
And then the last work here, which Graham already talked about 2 lectures ago, what is QLoRa. So here they use parameter efficient fine tuning to train a highly quantized like 4-bit model. And they do a bunch of other fancy tricks. And QLoRa is like super popular right now. So this is probably the if you're going to use a quantization method today, this probably would be it. Okay, I think I'm going to move on to pruning now. So any questions here?
When I have like 10 minutes of streaming left, if I start pruning, I think I'm not going to be able to finish it. So I'll pause here, copy the time so that we can come back to it later. Nice. And I feel like watching this video. I think I have not watched this syntax one on stream. I've probably watched it on my time. So,
hi, I'm Taylor and welcome to Crash Course Linguistics. In episode 3, we learned about how to test which parts of a sentence are constituents, or closely related subgroups of words.
Oh yeah, I learned that the word constituent doesn't have to mean election.
So in the sentence, Taylor sees the rabbit, we know the rabbit is one such constituent because we can substitute it for a single word or pronoun, like gavagai or them. And sees the rabbit is another slightly larger constituent, because we can move the whole thing up to the beginning of the sentence in a cleft construction. It's seeing the rabbit that Taylor does. Now, we want to take it a step deeper. Let's figure out a way to keep track of these groupings and extract some rules that could help us find patterns between lots of different sentences. This is by drawing. A simple way to keep track of different parts of sentences is by drawing connections between the words. For example, we could draw circles around each constituent, but circles get really big really quickly as our sentences get longer. Or we could draw brackets around each of the constituents. Brackets are nice and compact, but they can be hard to easily scan and understand at a glance. So instead, linguists often represent the structural relationships between words using a tree structure diagram, sort of like a family tree with nodes and branches. Tree diagrams strike a nice balance between being understandable and taking up a reasonable amount of space. The nodes represent links between constituents, so it's useful to label them. That helps us compare the tree diagrams across various sentences and track the different phrases in the sentence too. A phrase is a constituent that's sort of mid-sized. It's less than a full sentence, but often more than a single word. In this video, we're going to meet some of the common phrases that are the basis of English grammar. For example, the difference between the phrases sees the rabbit and just the rabbit is that sees the rabbit has a verb in it. So we can call sees the rabbit a verb phrase. Using the substitution test we talked about in the previous video, we can swap the positions of Taylor and the rabbit in this sentence. So they should both be the same kind of phrase. Since both of these phrases have a noun in them, we'll call them noun phrases. The word the, by the way, is part of a class of words that linguists call determiners, which also includes words like this, my, one, and every.
Many English speakers might only be familiar with the election sense, but would be able to guess more general meaning of something that constitutes. Yeah. Because, we get a lot of, just on the internet, a lot of election talk recently.
Determiners help us figure out which specific instance of a specific noun we're talking about. There's one theory of syntax that actually argues there are determiner phrases as well as noun phrases. Either way, these small words do a big job. So let's label our tree with the phrases and word classes to keep track of all of this information. And the whole thing, as we already know, is a sentence. Writing out noun phrase and verb phrase every time gets kind of tedious, so linguists generally abbreviate these as NP and VP. And the same goes with N for noun, V for verb, and S for sentence, plus det for determiner. Tree diagrams let us see the predicate relationship we talked about in the last episode. The verb and object noun phrase are both together within the VP. Even in languages that put their words in a different order.
I think right now VP stands for vice president and not verb phrase in my brain.
The verb and the object still have this closer relationship. Let's take Japanese, for example. In Japanese, the verb comes at the end of the sentence. The verb is still in the same phrase, the verb phrase, as the object. So we can represent this in the tree structure diagram by just giving the VP node a little twist. Going back to English now, here's another sentence.
So now I'm thinking in other languages. Korean is same with Japanese. The verb comes at the end. I think in Arabic, it's subject, verb, object. which is close to English. Because like in my brain, it's Tyler. Sees is Yara, and then the rabbit is what's rabbit in Arabic? Arnab. There we go. Yeah.
Gavagai ate my cake. This new sentence has completely different words from the first one, but it has the exact same structure. So its tree structure diagram looks the same. We can make a lot of sentences from just a few basic bits of structure. And this leads us to an interesting puzzle. Let's try to figure out all of the possible structures for sentences in English. In other words, let's try to make a grammar of English. A grammar is a description of how sentences go together in a language. We could use a grammar to start to teach machines to understand English or to compare the rules of English to those of another language. A grammar isn't necessarily what's actually going on in your head when you're saying a sentence. That's still an open question that linguists are researching. And while we'll be focusing on a grammar of English here—
Wait, when she said the word focus, did you see it go out of focus? That was not my eyes, right?
Open question that linguists are researching. And while we'll be focusing on a grammar of English here, every language has one. Making a grammar is actually a pretty big challenge. Let's start out with a few sentences and figure out how to describe their structures. Taylor sees the rabbit ate cake, and Gavagai hopped. First, we notice that we can split each sentence into two pieces, and we can mix and match the front half and the back half. We have Taylor, the rabbit, and Gavagai on one side, and sees the rabbit, ate cake, and hopped on
It's the thing and the action, right?
the other. This structure predicts that Taylor—
the thing that does the action and then the action. Okay.
Taylor hopped and Taylor ate cake and Gavagai sees the rabbit should be okay sentences, even though they're not on our original list. Based on my linguistic intuitions as an English speaker, that's a good prediction and is part of our grammar. We've established that sentences contain two parts. But what if we split those sentences up like this instead? This predicts that the sentences Gavagai ate rabbit, ate cake, and my cake should be possible. And we know as English speakers that they're not. We'd expect some group—
Rabbits like cake? I mean, if it's carrot cake. But there we go. That was a joke.
groupings to fail like this in any language we tried. So in our grammar of English so far, these sentences contain two parts, but it also matters what those two parts are. Let's go back.
I think the stream is really bad, right? I'll just finish this video and get out of here. Oh, feels somewhat better, but yeah. Sorry about that.
Grammar. First, we can say that a sentence in English is made up of two parts, a noun phrase plus a verb phrase. A noun phrase is made up of a determiner plus a noun, and a verb phrase is made up of a verb plus a noun phrase. But even though those rules are a good start, they still need a few tweaks. Not all of our noun phrases have a determiner in them. Sometimes it's the rabbit, but other times it's just cake. And some of our verb phrases don't have a noun phrase in them either.
Oh yeah, thanks, I'm back. I recall even too much carrots, much less case, aren't healthy for rabbits due to starch content. Oh, I'm guessing we're kidding. Cake is not good for rabbits, I don't think. I don't know. The joke is that there are carrots, so the rabbit likes it. Yeah. Did you guys know that carrots being good for our eye is a myth of the World War II thing? Like, they had radar, and was it World War I or World War II? And they were asking, the enemy was asking, like, why can they see our stuff? And they were saying because they eat carrots, they have good eyes. And the point was they had radar and they could detect them. Yeah. If we did that right now, we said we have carrots and our language models are really good. That would be funny. Yeah. Anyway, I'm not saying carrots are not good. They're great. But there is no direct correlation. White rabbits may turn orange? Really? Because I don't know that. Like, because of carrots? I have no idea of that. Whoa.
Sometimes it's sees the rabbit or ate cake, but other times it's just hopped. So we need to indicate that certain parts of these rules are optional, which we can do using parentheses. It has a nice effect.
Really? Even the Popeye? I mean, spinach is good though. Like spinach has to be good. Because it's a green. Wait, is carrot? I don't think carrot is a fruit because it's a root, and that rhymed. Wow. Yeah, that's the root of the problem. I don't mind the Popeye propaganda myth. I don't mind the carrot one as well. Like, it's just good food.
The only thing that's absolutely required in a noun phrase is a noun, and the only thing that's required in a verb phrase is a verb. We call the required piece, the part that the phrase is named after, the head, and the less important additions, the complement. There are plenty more things that we can add to a sentence, which starts to make a grammar even more complicated. For instance, take these ones. The rabbit with a scarf hopped, and Gavagai ate cake on the moon. You've added...
Yes, have heard that. That people's skin color changed. I think that was a Vsauce video. Oh my god, from the past. Yeah. Keratomania? Huh? Whoa. That's really interesting. Yeah, but like skin color changing. What? Oh, I was like, what? Your skin color can change with coffee? You meant the... Okay, sorry. Long-running medical shows like Scrub and House will have an episode. Eventually. That's cool. I guess I have not watched many of those medical TV shows.
Two new phrases, with a scarf and on the moon. These phrases contain a determiner and a noun, but they also contain a preposition, a word that shows the relationship of the noun phrase to the rest of the sentence. So now we can make a rule for a prepositional phrase, which contains a preposition as the head and a noun phrase as the complement. We also need to refine our rules for noun phrases and verb phrases to allow for optional prepositional phrases. So far,
don't we just call them object? Like the rest? I don't know.
Our grammar contains just 4 rules, but it's already really powerful. To find out how, let's get into the thought bubble. Hey look, Gav and I are inside a thought bubble. Let's go into another thought bubble. Cool, we're inside a thought bubble inside a thought bubble. Let's go deeper. Now we're inside a thought bubble inside a thought bubble inside a thought bubble. We could just keep going. We might get bored or run out of space on the screen or get cut off by YouTube's time limits, but in theory, we could just keep embedding thought bubbles inside of thought bubbles forever. Let's pop a few of these thought bubbles and get some more breathing room. Okay, leave thought bubble and leave thought bubble. Okay, now we're back in a normal single bubble. Thought bubbles have the property of recursion. We can embed thought bubbles inside of thought bubbles forever. Language is also recursive. Let's take the phrase inside a thought bubble. Inside is a preposition, so this is a prepositional phrase. And a thought bubble is a noun phrase. But inside this noun phrase, a thought bubble, we can add another prepositional phrase. Let's say it's also prepositional. It's also inside a thought bubble. And we can keep going. In fact, we already did when we were describing the recursive thought bubbles in the first place. We don't always have to embed the exact same words. Recursion just means we can build structures inside of other structures. For instance, the rabbit on the moon, in the solar system, in the Milky Way, in the universe, on Friday, hopped. There Gav goes. Thanks, thought bubble. And thought bubble. And thought bubble. Our simplified little set of 4 grammar rules is powerful enough for recursion, but there's also some things missing. Adjectives like big or purple, adverbs like quickly, pronouns like you or me. Sadly, this video does not actually contain infinite recursive space, but now that we're thinking like linguists, we can use our knowledge of language to continue to build up a more complete...
Noun is a person, place, or thing, verb, or action words. Yes. Yes. I remember my N's and V's. And then isn't it an O? I'm very sure, like, it's just like the rest of the sentence. That's what we were doing with it.
complete set of rules. This is just the start, but even with just 4 rules, we can see that sometimes completely different words have the same linguistic structure. Other times, the same words have different linguistic structures. We can see the similarities and differences by looking at language from the perspective of syntax. Let's take these 2 sentences. Time flies like an arrow means that the concept of time is fast, like an arrow is fast. Fruit flies like a banana means that these small insects are fond of fruit. Both of these sentences have flies and like in them, but these words have different structural relationships with the rest of the sentence. In this first tree, flies is the verb and like is a preposition. In the second tree, flies is part of the noun phrase and like is the verb. We can represent that difference by drawing diagrams. Don't stress about the triangles. Linguists use triangles within a tree to save space and represent constituents that are not the focus of what we're talking about.
Okay.
But we can see how these shared words occupy different parts of each tree. Or take the song about the mythical one-eyed, one-horned, flying purple people eater. This could mean a song about a creature that eats any kind of people and has one eye, one horn, flies, and is purple. Or it could be about a creature that eats one-eyed, one-horned, flying purple people, or something in between. Maybe a one-eyed, one-horned creature that eats flying purple people? Some of these beasts are a lot more dangerous than others. Throughout this episode, we've been using rules and tree diagrams as a fairly simple way of representing the structure of sentences. But there are lots of other ways of representing the same sentences. There are many theories of syntax which have different ways of representing grammatical structures, each with their advantages and limitations. And there are some grammatical structures that syntacticians haven't even figured out how to represent yet. So far, we've seen sentences with absurd meanings but reasonable grammar. Next time on Crash Course Linguistics, we'll go deeper into meaning itself. Thanks for watching this episode of Crash Course Linguistics.
You're welcome.
If you want to help keep Crash Course free for everybody forever, you can join our community on Patreon.
Nice. That was fun.
Hi.
Goodbye. Yeah. I think we did good today. Next stream I'll have to actually get to the fine tuning, but today it was mostly about evaluation. Rouge. So that was fun. I'm glad that I did that one. So now things are all ready. Like everything is ready for the training part, which will be next time, inshallah. And then let's snooze this ad break. And we did 20, that's funny, 25 minutes of a lecture, which is a lot, honestly. And then a video here. So I think that was pretty good. I'm happy. Yes. And I'm happy that I was able to stream this weekend. Weekend not over, but yeah. Okay, weekend is almost done. And during weekdays, I think I'm gonna try and adopt have a rest day middle of the week. See if that's possible. Thank you. You don't have to though. You don't have to catch up if you don't feel like it. Yeah. So see you next time. If there's anything, let me know. I'm around wherever I am. I don't know. And then thanks for learning with me. Yeah. Okay. I'm going to, what did I do? Oh yeah. I'm going to say goodbye, I think. Trying to find that hand wave gesture thing. Oh yeah, I think I forgot to add it the other day. Does that work? That has hands? Oh no, that's like, get away from me. Wrong one. Yeah. I will go now and then see you next time. Yeah. Ending the stream in 5. Oh, hi Michael. Hello. This half heart can be for you. This is a half a heart, by the way. Ending the stream in 5,